Analysis of the outer region, wall region, and fluid-solid interface in turbulent pipe flow. Introduction. The study of developed turbulent flows in pipes is of great measurements 3, oil film interferometry 2910, and micropillar shear stress sensors 1112. All these experimental methods have limitations and challenges too, which results in errors in their results. Empirical relations have been developed for the velocity profile in wall-bounded turbulent flows for smooth walls and rough walls 1-6. The velocity profile for a smooth pipe is given as Introduction. The study of developed turbulent flows in pipes is of great measurements 3, oil film interferometry 2910, and micropillar shear stress sensors 1112. All these experimental methods have limitations and challenges too, which results in errors in their results. Empirical relations have been developed for the velocity profile in wall-bounded turbulent flows for smooth walls and rough walls 1-6. The velocity profile for a smooth pipe is given as the wall shear stress, if not measured directly, for example by the new micropillar shear stress sensor, can be found by using pressure sensors and the equation. Influence on the wall shear stress and energy as indicated by eddies develop in the viscous sublayer and flow out to the other regions 3, 4, 5. Understanding the viscous sublayer may also be the key to understanding how drag reduction agents work 7. Where dP/dx is the pressure gradient. 0 can also be found using the coefficient of friction, with the equation 1. Specifically, the velocity profile of the viscous sublayer determines the wall shear stress 0, which is an important parameter for describing turbulent flows too. In experiments, it is not easy to obtain accurate velocity measurements within the viscous sublayer too, though there is a wealth of where v is the average velocity. Additionally, a simpler velocity profile which adequately describes the turbulent flow velocity in a pipe is the power law profile, given as 1. Experimental information on turbulence close to the wall. Experimental study of viscous sublayer has included visual observation using ultramicroscope 3.8, hot wire. Discussion. The results in Table 1 and Table 2 show that R1 is a separation between two flow regions. R1 clearly separates the outer region from the wall region. Table 1 shows that for turbulent flows in smooth pipes, the normalized distance from the wall at which the boundary between the two regions occur is always greater than 30 and increases logarithmically with increase in Reynolds number. Turbulent flow in a smooth pipe is therefore expected to have both a viscous sublayer and a buffer zone. Experimental investigators have reported that the wall/outer region boundary location is dependent on Reynolds number 1-2, but not as detailed as the result presented here. For turbulent flows in rough pipes, the results of the analysis shows in Table 2 that the normalized distance from the wall at which wall/outer region boundary exists is a function of the relative roughness of the pipe. In more details, the normalized distance from the wall at which the wall/outer region exists may increase or decrease depending on the combination of variation of the Reynolds number and relative roughness. The distance y represented by non-dimensional values y/d and y/r decreases with either increase in relative roughness or increase in Reynolds number. The observed trends can be explained by the relation between the variables as presented in equation 31, which shows that y_end is directly proportional to the product of re and the square root of f, and f reduces with increase in re before the flow is completely turbulent but always increases with increase in /d. Extreme values of y_end obtained, see Table 3, shows that y_end can go as low as 6.2, so for a turbulent flow in a rough pipe, there may not always be a buffer zone, 5y plus 30. Though y plus may be greater than y plus, R1, of y plus equals 5, it should not be used as a criteria for determining whether the smooth pipe friction coefficient equation should be used. Rather, the assumption should be made only when /d is extremely low, such that 0.725, 0.5, 76. In order to ensure that the error due to the assumption is less than 2.5%. It is assumed that empirical friction coefficient equation such as equation 75 is developed from experimental data that absorbed the effect of whether y plus is greater or less than 5. At the pipe wall, the turbulent flow is characterized by bursting from the rough wall 14 and sweeping from upstream 21, which all contribute to the turbulence production process. Enough information on the wall boundary condition is not yet available for a direct solution of the flow equations to find R1 and directly. Case 1 analysis for the smooth pipe is more accurate than Case 2 analysis for the rough pipe, since the effect of required more work and approximation as presented. The equations obtained for Case 2 could not be used to check that it drops to the equations of Case 1 by writing /d equals 0, since the validity of the empirical equations used did not cover /d equals 0 in its range of validity without significant error. Additionally, selected equations which were presented in small fonts to fit the half-page columns in Section 2 have been expanded in font size and present in a full-page column in the appendix. Conclusion. Theoretical analysis of turbulent flow profile in pipes has been made. Equations, which include the power law and other forms of solution to the Navier-Stokes equation, were fitted to sections of the flow field to eliminate the limitations of the power law at the center and at the wall. The outer region and outer region boundary or interface location was found for both cases of turbulent pipe flow in a smooth pipe and in a rough pipe. The boundary layer location trend and variation with Reynolds number and relative roughness was presented. The normalized distance from the wall to the outer/wall region boundary was found to occur at 21,295 for smooth pipes and 6,882 for rough pipes, with the combination of Re and /D determining its exact location. This work calls for further experimentation and measurements in the near wall region and at the wall that will provide information for further analysis. The result of this work can also be used as a guide during experimentation to know where to focus on for measurements.